Hello and welcome to part 2 of lecture 36. So in this part I kind of want to walk you through the proof of the singular value decomposition theorem. Now some of the details that we need we kind of skimmed over in earlier parts of chapter 7, but hopefully you can grab your textbook and see how all of the pieces go together. And so we're going to be using kind of a lot of the properties that we developed about the special types of operators like the self-adjoint operator, the positive operator. So you might want to have those results handy as we're going along. Okay, but I'll walk you through the proof. So we're taking any particular operator and we're looking at this square root, so the square root of t composed with its adjoint. And this is a self-adjoint operator. And so by the spectral theorem, because it's self-adjoint, there exists an orthonormal basis E1 up to En, such that when you plug E1 into the basis, you get S1 times E1 for all I, right? So just remember here that this is the eigenvalue of E1. And in fact, what the spectral theorem is telling you, right, is that when you have a self-adjoint operator, you have a basis of eigenvectors that are also orthonormal. Right? So we're really just using the fact that this is a self-adjoint operator. So that's kind of how we can do this. Okay. Now the other nice property is that since E1 through En is an orthonormal basis of V, what we have is that for any vector V in my space, if I wanted to write it in terms of this basis, one of the very nice properties of the orthonormal bases is you have an immediate way to write it in terms of the basis using the inner product, okay, provided you have an orthonormal basis. So V can be expressed in this way. So what we're going to do now is we're going to hit both sides of this expression with this operator right here. All right, so we take this operator and we're evaluating it at V. So the first stage that I can do is just replace V here with this expression in terms of the basis. Okay, so there's that property. Now using the linear property of the fact that this is a linear map and these are coefficients, I can pull all of these out. So I have V, the inner product of V and E1, and then this operator evaluated at E1 all the way to the inner product of V, En, and T star T evaluated at En. And then I obviously left myself more room up here and should have left myself some room down here. But each of these values here that show up, I can rewrite it in terms of an eigenvalue, right? So this is equal to VE1, S1E1, up to the inner product of VEN, Sn times En. So it looks like we're almost there, right? Because we have kind of all the terms here, but we're not quite right because it's not the right operator here, right? This is the operator coming from the square root of this operator, right? And we want this to be for t, right? So this is for t, but we only have this part, and we don't have the right basis on this side, but we get the right coefficients. So we're almost there. We're almost there. Okay, so the trick is now how do we fix it from here? Well, by the polar decomposition theorem, there is an isometry S such that we can write T as equal to S composed with the square root of this operator. Okay, that's what the polar decomposition theorem is, and we sketched out the proof. So what we can do now is we can now take that S, which we know exists, and hit both sides of this expression. So we hit this side, the first term, and the last term. Okay, so when we do that, we get, here maybe I'll use blue, we get S T star T, the square root of that, at V. And now S is just remember S is also a linear operator, so we can rewrite this as S1 was a constant, the inner product of V and E1, and then S evaluated at E1. And we can do this for each of the guys along here, right? So we have Sn, the inner product of Ven, and Sen. Okay, and I want to point out that on this side, this is just simply TV, right? Because of polar decomposition, we've taken T and we've broken it up into two parts. So we're almost there, right? Because now on the left-hand side, we have TV. On the right-hand side, we have all the coefficients, but now we have these E1 to Sen. Okay, but we were given that E1 through En is an orthonormal basis, and that S is an isometry. And one of the properties about isometries is that it takes one orthonormal basis to another orthonormal basis. So E1 up to Sen is also an orthonormal basis of V, okay? And this is a property about isometries, okay? And actually, if you go back and look at this section, you can find that this is one of the properties that you'll of an isometry. So why don't we just call this basis F1 through Fn? And so we can then take this expression right here and we can say, well, T definitely has to be written as S1 times the inner product of V with E1 at F1 up to Sn V, the inner product of V and En, and Fn. Okay, so we've done it because that's exactly what we wanted to prove for the singular value decomposition. Okay, so there's kind of a lot of slick stuff going on here. The slick stuff is to kind of first, cook up a self-adjoint operator. You get a nice basis, and then you notice, well, this guy here is almost T. I just have to multiply it by the right isometry, and the isometry doesn't destroy my orthonormal basis. It just gives me a different orthonormal basis. And there you go. At the end of the day, you get a different way of writing your map. So we'll do an example using matrices in the next part.